this talk and start this talk with an apology, because this talk is basically an attempt to advertise a paper that I published within a year. And that paper is Clays and the Origin of Life, the Experiments. So much of what I'm going to say in the first half of the talk is trying to give you an impression of what the paper dealt with in terms of clays in the solar system. What role do clays play in the solar system? So how did I even come to clays in the first place? Well, we're going to start off with a picture of what clays are, and then I will tell you why maybe I'll tell you why I came to it in the first place. In 1975, I published the following paper, Speculations on the Origin and Evolution of Metabolism. An autotrophic origin of metabolism is described, which compares clays. That's when it came in. When I worked on the origin and evolution of metabolism, that's when I came in contact with clays. So therefore, the point is why clays and why metabolism in a sense. Now, the reason for why metabolism and why clays is clays, when I came to study the origin and evolution of metabolism, it was clear that metabolism had evolved. It was not self-organization of metabolism. It was an evolved structure. Now, in order to evolve, you have to have an informational system that can replicate, mutate, and be related to natural selection. And that is why clays, and that was why I adopted clays as important in the origin of life. Now, clays are basically quasi two-dimensional structures, and they come in two varieties. One is kaolinite, which has got a tetrahedral layer and an octahedral layer, and the usual kaolinite is a very simple chemical compound. It's silicon SiO4 tetrahedra that form a two-dimensional plane. They are connected to the octahedral plane, and they are basically all aluminum. So a clay, like a kaolinite, is a silicon aluminate structure. This is now the smectite, and these are the ones that are of interest. And the reason that they are of interest is you have the tetrahedral layer, you have the octahedral layer, and you have another tetrahedral layer. It's sort of like a sandwich. The big point about these things are, in the tetrahedral layer, you can have silicon and aluminum, and they give you a charge on the surface of that system. In the octahedral layer, you can have a great variety of compounds. You could have zinc, yes.
So there's no iron in
Eh?
there are no iron acids.
In the middle.
Where are they?
Right in the middle between two layers, between two smectite layers is where the ions
That's
are.
where the iron is. Okay.
They depend upon the surface charge of the clays, and they depend upon substitutions of aluminum and silicon in the layer, we will come to clays that are much more interesting for the origin of life, which are based on iron and manganese and magnesium, as opposed to silicon and aluminum. Right now, we're sticking with silicon and aluminum. Now, in the octahedral layer, as you can see, you can have aluminum, you can have magnesium, you can have iron, you could have zinc. There's a whole variety of things you can have in the octahedral layer. And that depends and relates to the charge on the surface. So if you have a silicon, it's neutral. If you have an aluminum in that layer, then it's a negative charge. Now, in the middle of these things are the ions. This is a water structure, and it's got water in the middle, and you have cationic species, such as sodium, potassium, calcium. Those are the ones that are on Earth. So that is what a clay is. Now, the structure of a clay was not known until 1930. And it was here at Caltech, Linus Pauling used X-ray diffraction and worked out the structure of clays. And this is now looking at the surface of the tetrahedra. And you'll see that there's this hexagon structure. You can see here this hexagon structure. This is related to the octahedral layer below. Now, many years ago, I worked on, this is an illite, using the atomic force microscope. And what you could see there, it's a little blurry. You can see the octahedral layer. I mean, this is sort of was taken from this because of the blurry structure. This is exactly what was predicted by Pauling. I think it's the most, and there are now technologies and techniques to actually give you atomic resolution on the surface of the sun. So that is a very quick summary of what clays are and what their structure is. And the big thing is that in the smectite family of clays, you have this enormous variety, both at the tetrahedral layer and the octahedral layer. And that relates to how powerful they are as catalysts. Kaolinite is not a catalyst. It's not a good catalyst. Smectites are very good catalysts. And just to tell you how good they were used before they did zeolites, mainly in the petroleum industry for cracking. And they have been used in many areas for catalytic reactions, especially in chemical engineering. So if you want to know about clays and organic chemistry, go to chemical engineers.
Do we think of them as being sort of rigid solids? Because when we think about clay normally, you think of like a grey, squishy, hydrated material. Should we think of them as a solid sort of crystal structure, or is it more?
It's as their crystal structure. These are not, when you think of clays as soft, it's because given the water between these two layers, they move around like crazy.
Right.
And one of the problems is that if you ever are in a road with mud, etc., and it rains, then that's why your tires go round and round, because the clay particles move with respect to each other. So clays in the solar system.
Does that make it more difficult, like this sort of retention of water, make it worse, sort of catalyzing condensation reactions, or does it,
Well, it depends. I mean, obviously, when you have clays in nature, you have water. I mean, that's the sine qua non. I mean, unless they form micas and have been, dried out. I mean, micas were, if you have potassium in the interlayer, then the bonds between these things get very sharp because there's no water around the potassium, whereas around sodium, there's a lot of water. Sodium lives in a water clathrate and potassium does not. So when you have potassium, the bonding between the clay layers is very strong. There are micas. That's where you find micas. And that was what he worked on, by the way, was on the mica, because that's a very rigid structure. Okay, where do you find clays in the solar system? And what type of clays are you finding? And how do they relate to organics on the various bodies of the solar system? Now, in the paper that I wrote on clays and clay minerals and the experiments with Theo Klaprow, I basically went a lot of time on this idea of where in the solar system it occurs. Now, here is Ceres. This is the largest body, dwarf planet, in the asteroid belt. And it's been recently studied by this mission called Dawn. And so I'll read to you sort of one of the consequences of what it says. Although Ceres is not actively discussed as a potential home for microbial extraterrestrial life, as Mars, Europa, Enceladus, or Titan are. Yukyung and I have worked on Enceladus. It has the most water of any body in the inner solar system after Earth, and the likely brine pockets under its surface could provide habitats for life. It does not experience tidal heating like Europa or Enceladus, but it's close enough to the sun and continuous long-lived radioactive isotopes to preserve liquid water in its subsurface for extended periods. The remote detection of organic molecules, compounds, and the presence of water mixed with 20% carbon by mass in its near surface could provide conditions for favorable to organic chemistry. Of the biochemical elements, Ceres is rich in carbon, hydrogen, oxygen, and nitrogen, but phosphorus has yet to be detected, and sulfur, despite being suggested by Hubble UV observations, were not detected by Dawn. So the mission to Ceres was done by Dawn. It was so successful in terms of adding new questions that there's now another mission to Ceres. And so the Chinese also have a mission to Ceres. And what they want to do is get sample return.
Can you tell us about the chemistry of those atoms? Nitrogen, sulfur, carbon, so on.
So he was asking if you can tell the chemistry of this items?
Well, I don't know. I mean, that's one of the problems. It's still somewhat mysterious.
So you don't know what is
what-
carbon?
So the problem really is they have to go back.
After what is the carbon?
I
Pardon?
mean, what
They
molecule?
don't know the nature of the carbon. You cannot say they're amino acids or any specific. All they could do is get some reflectance spectroscopy. They didn't land on it or anything else like that. The one thing they did pick up were clays, which is my major interest at this point. Now, the clays they picked up with was interesting. The counter ion in the clay was not the usual potassium or sodium or calcium. It was ammonia. It was the ammonium ion. And this is very interesting because in order to try and explain where the ammonium ion came from, they believe that Ceres may have been formed not in the asteroid belt, but from more outside the asteroid belt, and then came into the asteroid belt. But anyways, Ceres is obviously a great place for looking for what happened on dwarf planets with water and a lot of history. And it's going to be looked at again. So I'm looking forward to the looking. But the one thing they did find, which was so surprising, was ammoniated clays. And you could see them related to the phyllosilicate. Here is the phyllosilicate abundance, and here is the ammonium. Now, this takes us to the asteroid belt. And there are a number of, now remember, Ceres contains 42% by mass of the asteroid belt. And if you put these other ones in, you're getting up to 80 to 90% of the asteroid belt mass. Vesta was also looked at carefully at that time, and it had very interesting stuff to talk about. So these bodies, the four largest asteroids, are really of great interest to the origin of life and to the evolution of clays and organics. Now, I want to now talk about carbonaceous chondrites, for which we know a lot more. The carbonaceous chondrites as analogs for the composition and alteration of Ceres. So the carbonaceous chondrites have come from some planetoid-like body. And they just broke up into pieces. And the question is, what do they tell us about these bodies? Now, the carbonaceous chondrites. This is the Murchison meteorite. It was a big meteorite that came in and then broke up into fragments. This is one of the biggest fragments. And it fell into Murchison. It belongs to the carbonaceous chondrite class, a group of meteorites rich in organic compounds due to its mass over 220 pounds, 100 kilograms. And the fact that it was an observed fall, the Murchison meteorite is one of the most studied of all. Thank you. Here is what they found in terms of organics on the meteorite. Amino acids, that number has now grown to over 100 different amino acids. Aliphatic hydrocarbons, which they think was made on the surface of the thing. aromatic hydrocarbons in great abundance. Fullerenes, the famous fullerenes. Carboxylic acids like oxalic acid, etc. Hydrocarboxylic acid, a very tiny amount of purines and pyrimidines, alcohols, sulfonic acids, phosphonic acids, and as you see, as you go from down up to down, these are really in minor quantities. And the total is, these are the parts per million found on the meteorite. Now, the major thing that people have looked at, and the ones I'm going to discuss, are basically the common ones that are found. And the ones they found were glycine, alanine, glutamic, and a number of the other 10, there's about 10 of the biological amino acids found. And they are all DNL. There's no chirality. A specific family of amino acids called diamino acids, like glycine, and another set of them, which I will talk about later, are also found.
Can I just ask a question about the size distribution of all these molecules? So there's clearly a huge diversity of organics and related molecules. And so, you know, it is interesting to look at Merson meteorite as an experiment in prebiotic chemistry. So if we were to just plot a histogram of the molecular size, I guess there's going to be some cutoff.
No,
So I'm wondering basically how big, like what the biggest molecules, because there aren't any peptides.
the biggest molecules are the polyaromatic hydrocarbons.
Okay, so there's
And then there's a huge amount of complete insoluble material. These are all soluble.
but there are no, for example, like peptides with two amino acids polymerized together.
As far as I know, I don't know anyone who's claimed a polypeptide.
So it's all bonds, basically.
The major point of this is that the amino acids and the carboxylic acids are all correlated with the hydrothermal alteration on these meteorites. That is, that tight coupling between the clay that are forming on these meteorites and the soluble ones, like oxalic acid or amino acids. Okay, the hydrocarbons are being synthesized by some other mechanism, and I mean, there's a lot of stuff coming from the solar system before the thing differentiated into. So it is the things that are soluble that are related to the hydrothermal system. That's what is of interest. And I'm just going to talk to you a little bit about this oxalic acid, which was found on the meteorite by Jim Lawless. And the interesting thing is I worked with him at NASA Ames for 3 summers, and I really enjoyed my time there. It's not going. What's the matter? Okay. Now here's the point which turned me on to this thing really strongly. Carbon, hydrogen, and nitrogen isotopes in solvent extractable organic matter from carbonaceous chondrites. Here at Caltech by Becker and Epstein. So they did this, and they used carbon tetrachloride and methanol and or water to extract the soluble material on the carbon. And they looked at isotopes, et cetera, but here's the key point, and this was also found at NASA Ames when I was there by Bunch and Chang. A relationship is suggested between the event that formed hydrous mineral in these two meteorites, and the introduction of water-soluble organic compounds. Those were the amino acids dominating. Now, why is that of interest? Because the most important thing that's happened in carbonaceous chondrites in recent times is that the enrichment of amino acids it's covered over. The enrichment of amino acids in it depends on the aqueous alteration on C1 and CM meteorites. That is, the more hydrothermal alteration, the more clay, the more enrichment of amino acids, and in particular, it's the isovaline. It's not a normal amino acid. Now, this is of such importance because for you guys, if one of the things you might look for, if you ever had a chance to get to the amino acid composition, is biosignatures. Is the amino acids you find on these planets D or L, or complete, 50-50. Well, you ought to look at this review. It just came out 2020. It's an interesting statement about whether or not you can use these biosignatures once they found them on the carbonaceous complex. Now, in the most recent meteorite, the Taglish Lake meteorite, they found 100% L aspartic acid. That means this thing is really of interest. One of the deepest problems in the origin of life is, where does the chirality come from? Why are there L amino acids and why are there D sugars? Mars. Well, Mars is of interest because they found clays. And why is finding clays on Mars so important? Because the area where they found the most interesting clays are between 4 billion and 4.5 billion. Now, the biggest problem we have on the origin of life in terms of a memory in the geological record is that we're missing that exact amount of time on Earth. And the hope has always been that Mars may have retained a memory, since it doesn't have continental drift, etc., that it may have retained a memory of that period. So that is a very great important step on Mars, as far as I'm concerned. There's a lot more about Mars. There's a lot more going on. I have a book here, anyone's interested in, is that a book on that the greatest mystery of all time is the discovery of life on Mars. So it's a really nice book. The Earth. Well, here's a paper. The iron-rich clay microsystem in basalt chromatic lavas, importance of iron smectites for prebiotic molecular catalysis during the Hadean era. And this is Alan Munier, who's been working on these clays on Mars right now. During the Hadean to early Archean period, precisely 4.5 to 3. The surface of the Earth's crust was predominantly composed of basalt and chromatic lavas. The conditions imposed by the chemical composition of these rocks favored the crystallization of iron and magnesium clays, rather than aluminum and rich clays, which we find on Earth. Iron magnesium clays were formed inside chemical microsystems through deweathering or hydrothermal alteration. and for the most part, through the post-magmatic processes. This is of interest because when you look at the stuff that they found on Mars, the clays broke up into continental, sedimentary, and layered. And it was the crustal ones that were iron and magnesium rich. And this is, he goes on to say, considering the high catalytic potential of clays, and particularly those of the iron-rich ones, electron exchangers, it is probable that large parts of the surface of the young Earth participated in the synthesis of prebiotic molecules during the Hadean or early Archean period, through innumerable clay-rich microsettings in the massive parts and the altered surfaces of hematite and basaltic lavas. This leads us to suggest that iron magnesium clays should be preferred to aluminum-rich ones, montmorillonite, to conduct experiments for the synthesis and the polymerization of prebiotic molecules. So what comes from the from Mars and the planets, iron-rich clays and coupling of these clays to organics, ultimately leading to chirality. Okay, so what is the problem of the origin of life? In Earth science, a geochemical cycle is the pathway of elemental elements taking the surface of the Earth. A biogeochemical cycle is important in forcing organisms include water. Important for living organisms include water, calcium, carbon, nitrogen, phosphorus, and sulfur cycles. The origin of life is how does a geochemical cycle become a biogeochemical cycle? That's the problem. And here is sort of the rock cycle, and then there's the water cycle, and it's the coupling between these two cycles that lead to clays. Dominant. And this was from a book on sedimentary geology. Clays, which are sheet silicates the size of colloidal particle viruses or the particles of smoke from a cigarette, are the most abundant minerals on the surface of the Earth. Clays cover about 75% of the land surface and blanket most of the deep sea seafloor in pelagic oozes. That coupling between the geochemical cycle, which is the rocks constantly being going, and the water cycle, are the cycles that where life occurred. That's where clays occur. Now I'm going to, in the last 10 or 15 minutes, go into a lighter subject. Now, that thing that I just discussed was an advertisement for my next talk, which is how do clays relate to the origin and evolution of metabolism? Because the solution to the origin of life is based on two major invariants. The first one is the origin evolution of metabolism, and the second one is the origin and evolution of the genetic code. Now, the problem we have in sort of geology is we don't have the records that go back to between 4.5 and 4 billion years ago. But we do have the record in life itself. We do have the record in metabolism, that you can work back in metabolism as it exists now and to the origin of metabolism. And the same thing is true about the genetic code. And that's now, the next lecture is the intersection of how what you can do within biology, how it intersects with what happens with clays, especially iron-rich clays. Now, the part two is a much lighter story. How I came to clays and what happened next. I told you how I came to clays, and now the question is what happened next. So I told you that I had written this paper, and I said an autotrophic origin of metabolism is described, which requires clays, transition state metals, disulfide and dithiols, UV, and I no longer believe cyanide ion. Now, the reason I came to clays was this guy. This is Graham Karen Smith. He is the founder of the idea that clays replicate, mutate, and are selected for. He is the guy who did it. So the origin of life, according to the specific theory that is proposed, the primitive genographs were patterns of substitutions in colloidal clay crystallites. The theoretical information density in such a crystallite is comparable to that of DNA. Evolution proceeded through selective elaboration of substitutional genographs that had survival value for the clay crystallites that held them, at first through genetically controlled adsorption of organic molecules within a complex dynamic primitive environment, a gradual takeover of the control machinery by organic macromolecules. A genetic metamorphosis is then considered to have occurred. And here is what he thought might happen. Yeah, you would have a positively charged on one surface, attract the negative one, then a negative one would attract the positive ones, et cetera, et cetera. So Karen Smith said clays can replicate. This means, and have catalytic ability. This means that they can evolve. And this guy, Isaac Barshad, was at UC Berkeley in the soil department, which I then spend a fair amount of time talking to. And he then gives you the actual thing about how it may have occurred. So the formation of clay minerals in soils, that is the interesting fact. When you talk about soils and organics on Earth, you're talking about clays in soils. Just as it's believed to be catalyzed by other minerals of the soil through the absorption of these products on their surfaces. The surfaces of the existing clay minerals or primary minerals may be considered as nuclei, which initiate the crystallization process. This is exactly what happens in DNA or RNA. Crystal lattice growth may be said to begin with only a few silica tetrahedrons are observed on the OH surface of a kaolinite, or a few molecules of alumina are absorbed on the oxygen surface of a mica, or montmorillonite, or a kaolinite particle. These absorbed molecules would tend to become oriented in a pattern similar or complementary to that of the substrate and become condensed through dehydration into two-dimensional sheets of linked tetrahedrons or octahedrons. At any one time, crystal lattice growth may proceed in the direction of any one of the crystallographic axes, depending on the availability of reactants and conditions favoring absorption, condensation, such as pH, moisture, presence of chelating substances, and possibly other conditions. That is, he now in soils, independent, in early days, before Graham Karen Smith, basically gave you the fact that the clays replicate. Now came this great man, Armand Weiss. Armand Weiss published a paper in 1981, in which he says, using layer silicates as models, the principle of replication, the spontaneous self-multiplication of a carrier of information can be shown to be a general property of certain macromolecular systems. Errors in replication and feedback together with environmental influences may lead to mutants with higher or lower replication rates, thus enabling evolution. In the light of these findings, the question of whether or not chemical evolution resulted directly in the nucleic acid protein system, the genetic principle common to all living systems known up to now, has to be answered. It seems conceivable that as a first step, a much simpler replicating system was formed. Such a system might then have undergone an evolution of replicating systems, resulting in the final nucleic acid protein system. As a result of this talk in 1981, as a result of this paper in 1981, I convinced John Lewis, who was at MIT, and I wrote a proposal to NASA and to the Gordon Conference, and we founded the Gordon Conference for the Origin of Life, which is still going on. So I am really the founder of this Gordon Conference as a result of that paper by Armand Weiss. As a result of that meeting in 1982, we resolved a meeting in Glasgow the year afterwards, 1983. And we had 25 people that we invited, and they each gave a talk, and we all agreed to write up a paper. And of course, Armand Weiss was invited, because now he had done the experiments that showed exactly what Karen Smith had claimed. He had clays, he was replicating them, they were mutating, they were carrying out catalytic abilities. Now remember, Armand Weiss is the major clay chemist in Europe. He was head of the department in Munich. So this is gold. The origin of life solved. Everything is great. So that book, which I recommend, came out of this Glasgow meeting. There were 25 people invited, 24 papers came in. The 25th paper, which was supposed to come in from Armand Weiss, never showed up. And I visited him in Munich. I talked to him on the phone constantly. And every time there was a catastrophe that prevented him from finishing the paper. There was fire, there was floods, there was, it's got to be absurd. So so founding the Gordon Conference, the origin of life solved, because you have this system that is now. So of course, the people like Stanley Miller and Leslie Orgel thought they had to look into this, okay. And he had listed a number of papers that he had done in this thing. And anyways, To make a long story short, Professor Armin Weiss, in a paper published in 1981 in the Angewandte Chemie, has claimed observations with potential importance for the origin and early evolution of life. This paper has been widely, and since it claimed experimental proof of clarity, et cetera, where is it? Where's the, so, and guess who signed it? I mean, you know, it was signed by Gustav Arrhenius, Karen Smith, myself, Stanley Miller, and Leslie Orgel. Okay, that paper was wiped off the face of the earth. You ought to read the paper. It's a really good paper. It did found the Gordon Conference.
Hyman, this is Andy. I just put something in the chat. So if you have any time before you say goodbye and they kick us out of the classroom, take a look at the chat.
He asked where does the energy come from and what role
Where does the
Yeah, I've had my hand up on the Zoom for a little while, and Professor Hartman, I think.
well, the energy eventually, I mean, I deal with that in my next talk, by the way.
Yeah, let's,
It comes from light.
please allow enough time for Q&A at the end of each session. And I did want
I'll
to
be
just,
happy to, but let me finish this talk because
Well,
right now, I just wanted to
it's
end
5
up
minutes to 1. You
with
got to
with
finish
an
soon.
experiment. All right, I want to talk to you about one experiment that I did in 2009. Yeah,
Well, I was just wondering what happened with Weiss's experiments, like, could they ever be?
they've never been repeated. They were never done. I mean, Weiss was sort of like a King Leopold. He essentially, he lived in his imagination. This happened to him with other problems. Anyways, it was, I hate to say this, one of the great dramas of my life to try and dump that paper, because that paper solved the problem if it was repeatable. So I've gone on to try and repeat that experiment, but not his experiment. So I just want to talk very quickly about the formation of replicating saponite, which is an iron-rich clay, from gel in the presence of oxalate. Now, this is now being generated because of what happened on the carbonaceous chondrites. Implication for the formation of clay minerals and carbonaceous chondrites and the origin of life. Why doesn't this I just want to very quickly, I have 5 minutes and I want to finish off this thing. All right, so with the potential clay in the ABR has been a subject of debate for the last decade. The debate has centered on the clay minerals which are found in the carbonaceous chondrites. These clays are formed due to the aqueous alteration of chondrules containing anhydrous mineral phases like olivine, orthopyroxene that are found in these mirrors. There's a strong correlation in the occurrence of clay minerals and the presence of organic compounds. So I went to Colorado, Boulder, and worked with Dennis Eberl. And we set up an experiment where we put in oxalic acid and alkaline conditions with a gel of aluminum, enough to make clay. And not iron clay, but aluminum silicate clay with magnesium. And we did another one just with the alkaline, no oxalic acid. And then ran it for 3 months at 60 degrees in a tube that kept rotating. And the result of it is the oxalic acid catalyzed the clay formation way beyond the just alkaline instances. Now, what we also showed was that there was replication going on. And the way they showed it is you have clays that have low charge, that means charge on the surface, and high charge, even higher charge. And the way you check this is you take this organic molecule, which has a positively charged side chain, positively charged, and it's got 18 carbon atoms. And you now adsorb it onto the clays. So in low charge, this thing just lies flat. In high charge, it forms this vermiculite with a pseudo molecular arrangement. That funny thing up there, or even this thing. When you do with very high charge, you form this bi-layer. So if you add this compound to your clays, you can tell whether it's high charge, low charge, or medium charge. And here is what the clays look like on the system that had evolved. And here you can see that the depending upon the charge, you have a distance between the clays. This is high resolution electron microscopy. So if you have 31 things, it says that you have high charge. And if you have smaller things like this, you have low charge, they're flat. And so coming from the same gel, with the same compositions, you get these very different systems with high charge and low charge. And it's coming from the same gel under the same conditions.
Are there differences in growth rate?
What?
Are there differences in growth rate between these different sort of types?
No. I don't know. I mean, there's no right. This is the end of. Okay, so I just want to end there. That is, we've done the experiment with oxalic acid, and it's given us an extremely interesting result. So I end up with the experiment. Okay, I'm done.
Oh, yeah, thanks everyone. Sorry, today's a little bit disorganized and we have. Yeah, so we have the class right after this, so I have to end this.
Okay.
But if you have any question, you can
Okay,
bring up
hey,
next
Doc.
week. Dr. Hartman will be here next Wednesday as well. Thank you.